Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we are going to talk about build systems and demonstrate how we configured CopperSpice so it can be linked into a C++ application. Build systems. We are going to compare CMake and AutoTools and talk about their origins and where they are today. Then we're going to give a brief overview about how to build CopperSpice. Kitchen Sink is a sample program which is used to test the CopperSpice libraries and show what CopperSpice can do. We are going to show in detail the build files for Kitchen Sink.
The two most popular build systems in use today are CMake and AutoTools. They definitely have their advantages and disadvantages, but keep in mind that the process of building is extraordinarily complex, and in any given project, one may have a significant advantage over the other. This means there is no right answer choosing between CMake and AutoTools. There is just what fits best in your scenario. So how do you choose? Well, you could use what you know, or what your project already uses. Inertia is always a safe bet. You might try a new build system because you're sick of the one you're using. You might even try developing a new build system for the same reason. But at the end of the day, all of the time you spend setting up the build system on your project is wasted because it's not actually writing code. Unfortunately, it's not optional. Maybe the most important thing to consider when you choose a build system is how well it supports the tools you need for your project and the communities that you're involved in. The AutoTools build system was developed in the 90s, and it was developed to solve the problems that were most prevalent in the mid-90s. The main problem facing software developers at that time was the fact that compilers were not consistent or reliable, and they didn't conform to standards. AutoConf provided portable implementations of many of the more complex C and Unix functions so that they would be available on every platform. AutoMake provided a way to write your Makefile once and use it on every vendor's Make utility. And libtool allowed you to deal with the complexities of shared libraries because they were treated differently on every flavor of Unix. At its heart, AutoTools is really designed as a Unix tool. It was not ported to Windows until the late 90s, and the Windows support in AutoTools is always second class to the Unix system.
AutoTools has been around for a very long time, which means there are many good examples available. When you run into a problem, it is likely someone has a workaround. At the beginning of our project, we wanted to use AutoTools to package the CopperSpice source. We ran into a very strange issue with a line length limit in Bash. After a bit of searching, we were able to find an example which addressed this exact issue. It was in French, but it was very readable. Initially, we blamed AutoTools for this problem, but it actually isn't a problem with AutoTools. It's a limitation in Bash. The real problem is that AutoTools uses several external programs, which may have their own limitations, and this can in turn break your build. The CMake build system is similar to AutoTools in that CMake generates files which are used by your build tool. The build is actually done by some other program or utility, like Make or Ninja or even your IDE. This reduces the number of dependencies CMake has to work with. We did a bit of research on the origins of CMake, and what we found was their desire to solve the problem of maintaining build files on Unix and project files on Windows.
This is actually a very serious problem because maintaining the Unix Makefiles and the Windows project files side by side creates a lot of hassle for developers. It causes a tremendous amount of inertia in the project because it's difficult to do something as simple as adding a new source file. A major advancement in the goal of having a unified build system was developed in CMake in 2016. In version 3.7 of CMake, they added CMake server mode. This is a mechanism where an IDE or some other build tool or any application that needs information about your project can run CMake as a daemon and query information about the system that you have defined. This provides an accurate view of the exact build steps that your project requires. And this decouples the tools that you use from the implementation of CMake. So prior to the CMake server mode being available, when you were working with a Visual Studio project, you had to invoke CMake to generate a Visual Studio project file. This was certainly better than maintaining a separate set of Makefiles and project files, but it was still an additional step. Now with the server mode, you can open a CMake project directly in Visual Studio, and there is only one single set of files that needs to be maintained. This is referred to as native support for a CMake project. Another advantage of this server mode is that it makes the build process information available to tools which previously had to parse CMake files. This allows things such as documentation programs to find out information about include paths. This allows other build tools to discover when things are out of date or when CMake should be re-invoked to generate the build files again. This creates a more reliable integration between your tooling and the build system. With the introduction of the server mode in CMake, several major IDEs have added native support for CMake projects. This is important because it improves performance because there is not a separate CMake generate step. It also improves the accuracy that the IDE can present to the user because it has more information about the structure of your project. In contrast to AutoTools, CMake is a very simple language, and providing CMake macros is fairly straightforward. Writing an AutoTools macro can be quite challenging and complex. CMake also has excellent handling for dependencies, in that it understands which version of C++, which include files, which libraries, which functionality each build target requires, and it can propagate that information to downstream build targets automatically.
CMake is the central tool used for building a project. The other tool you should take a look at is CPack. This is used for packaging and distribution of your binaries.
One of the downsides of CMake is the fact that since it is a relatively new product, the available set of examples you can find is limited. This can be frustrating as a new CMake user because it's difficult to know who to trust and whose examples to emulate. Not to belabor the point, but since the CMake examples that are available are so limited, it would be very nice to have good documentation. Unfortunately, the official documentation is very weak. It is descriptive, and it says how CMake works and what the features do, but it provides no guidance as to the best way to put these features together to create the build system that will work for your project.
We don't want to put CMake down, and we strongly believe it is far easier to improve the documentation for the product than to write another build system. CMake version 2.8 is when the product became viable for most developers. As we mentioned, version 3.7 is when the server mode was added. What's encouraging to us is seeing that they actually have a nice release cycle, and there are 3 major releases done per year. In July of 2015, we had a wonderful contributor to the CopperSpice project who wrote our CMake files for us using version 2.8.11. In May of 2016, we upgraded to version 3.4.3. Our intention is to move to CMake version 3.7 around April of 2018. With Debian stretch out and Ubuntu 18.04 being released in April of 2018, we are going to move to at least CMake 3.7. We may elect to move to an even newer version of CMake, depending on what versions are available at the time.
In 2012, when we started CopperSpice, we used AutoTools because that was what we had the most experience with, and CMake was not quite ready. We currently support both systems and will continue to do so, since they both have environments where they are a good fit. We do reserve the right to change our mind, and it is possible that at some point we may deprecate the AutoTools build. We have made a commitment to the CopperSpice contributors and users that anyone who wishes to contribute changes to CopperSpice need only update one of the build systems. We are quite happy to maintain both of them and keep them synchronized. We're not the only project that's facing this dilemma. There are many other open source projects that have already moved to CMake or are seriously considering it. One of the largest debates was in the Boost community, and as of this July, they have made a commitment to switch to CMake. This is going to be a lengthy process, as Boost is a very large and diverse collection of libraries, and Boost is built using its own in-house build system currently. If you are the maintainer of a C++ project, and you're considering switching build systems, we strongly recommend that you look at CMake. It seems to have the most momentum among the C++ user community of all of the build systems that are available.
On our website, we have a CopperSpice overview documentation, which contains a lot of information about how to get started with CopperSpice and what the project is all about. One of the sections in this documentation is how to build a CopperSpice project. Hello Lunch is a very small project that we use in our CopperSpice overview documentation. Sample project files for CMake and AutoTools can be found in this documentation.
We want to show a real project and how it's built with the C++ CopperSpice libraries. This information that we're going to show applies to any C++ project that uses a library. A lot of times people will show the actual build files, but not the commands that would be used to invoke the build process. We'd like to start by showing you how the build process is invoked for the kitchen sink project. Note that when we're using the AutoTools build system, we have to export an environment variable called CSHome. This is used so that the kitchen sink build system can find where the CopperSpice libraries are installed. There is really no mechanism built into AutoTools to find libraries that are installed on your system but not in the default directories. In CMake, there is a built-in mechanism to find libraries, and so all we need to do is specify the CMake prefix path, and the CopperSpice libraries and all the definitions needed to use them will be found automatically by CMake.
These are the 4 files that are used by AutoTools to build Kitchen Sink. If you're interested in the contents of these files, they are part of the project. What we want to show are the actual project files used to build Kitchen Sink with CMake.
In a project that uses CMake, you will have a CMakeLists.txt in the root. You may also have one in your source folder, one level down. In the kitchen sink project, we also have subfolders below source. We have 5, and we're going to show the audio CMake file that handles that subfolder. We're going to start with the root CMake file. We've removed a few non-essential lines for clarity, such as the build timestamp used in kitchen sink. The first line of your CMake file should always set the minimum version of CMake that you require. This is important because it ensures that the functionality you need will always be available. On the second line, we set the name of this project. We then include some macros that are built into CMake to check various portions of the compiler and the include files that are available. The find package call will look in the default system directories and the CMake prefix path that we specified, looking for the CopperSpice package. When it's found, the CopperSpice macros will be instantiated, and all of the functionality provided by CopperSpice will become available in your CMake project. We then set some version number information and specify which parts of this project we wish to build. The next 5 lines of this CMake file provide metadata about the package we are building. Following that, we have 4 lines that configure various options in CMake. For example, CMake include current dir means that in each case, a source file will be able to include header files that are in the same directory. We also set that we wish a standard compliant compiler and that it make available the C++14 standard. We then set the output location where binary files will be built. And finally, we call add subdirectory so that the CMake file in the source subdirectory will be read. This is the CMake file for the source folder. The first line sets a variable that will be used to link with a specific version of CopperSpice. The next few lines show how to test functionality available on the build system. In this case, we are looking for whether the windows.h include file is available. The next part sets up a list of include directories. This is the list of directories that will be turned into -i commands for your compiler, so that headers can be included from these locations.
These 2 sections of the file set up the source files that are part of Kitchen Sink. For simplicity, we did not list all of the H files or the CPP files. The next 5 lines in the CMake file include the CMake files in the subfolders that are below source. The CopperSpice resources macro is part of the CopperSpice package. This macro will generate a call to the appropriate resource compiler based on the extension of the file. For example, a UI file defines a GUI, and the user interface compiler will be invoked. The add_executable command is very important, as this is the command that sets up what binary should be generated. The target include directories command is the preferred way of specifying include directories. This command sets the include path for only the Kitchen Sink executable instead of the entire build file. The target_link_libraries specifies which libraries should be linked with Kitchen Sink. CopperSpice::CS core looks like a C++ namespace. This is the syntax for linking with a library provided by a third-party package. The last few lines of this CMake file simply show how to turn off the console on Windows.
The last file we're going to show is the one from the audio subdirectory, and this one simply adds file names to the includes and sources variables that we set up earlier.
All of the source code for Kitchen Sink, including the AutoTools build files and CMake build files, can be found on our GitHub repository.
For more information about CopperSpice, please visit our website at www.copperspice.com.
Thanks for watching our video. We hope you found the content of value. If you have any questions, feel free to email us or leave us a message on our CopperSpice form. We'd love to hear back from you.
Please make sure you subscribe to our YouTube channel and come back in 2 weeks for our next video.